In the last chapter, we developed the notion of the derivative, the instantaneous rate of change of a function with respect to a variable. We were a little prohibited from doing interesting examples, or really good examples, because it was so complicated to actually calculate the derivatives from the definition. In this chapter, we're going to develop a set of rules. Fairly easy rules to remember that will enable us to calculate derivatives as fast as we can write for essentially any function that you'll encounter, or that one typically encounters in math, physics, engineering, in most fields. Yes, you can define strange functions that, in pieces or in some bizarre way, but the standard functions that we deal with will have easy rules for calculating derivatives of all kinds of combinations of them. So the first function that we would like, the first class of functions, in fact, that we would like to have a rule for the derivative of are powers of x, where the power is a positive integer. So we want the power rule. It's not called the power rule because it's so powerful, although it is powerful. It's called the power rule because it deals with the function x raised to powers. So the power rule. It simply says the derivative of x to the n is n x to the n minus 1. And right now I mean this where n is a positive integer to a natural number. So, 1, 2, 3. All right. This is the power rule. It says that the derivative of x raised to a power, you bring the power down and multiply it times x raised to one smaller power. So you bring the power down as multiplication and you subtract 1 from the exponent. Why is this true? Why would we make up such a strange rule that the instantaneous rate of change of x to the n is in x to the n minus 1, or the derivative of x to the n is in x to the n minus 1? The answer is we don't make up the rules that we're going to derive. You have to prove them from the definition of the derivative, the definition that makes the derivative the instantaneous rate of change. You prove them, but then you just remember the rule and you don't go back to the definition and recalculate every time. So why is this true? Maybe before I say why it's true, let me just give some quick examples that show you how easy this makes things. So what am I saying the derivative of x raised to the 4th power is? It's 4. X to the 4 minus 1, so it's 4x cubed. What's the derivative of x to the 17th? 17, x to the 16th. It's just, you can calculate the derivative of x to the n from the power rule as fast as you can write. All right. While I don't want to give a detailed proof, I'll give almost the entire proof of the power rule, just because you should have some idea of where it comes from, and always appreciate that we have to go back to the definition of the derivative to derive any of these formulas. So why is the power rule true? It relies on expanding binomials raised to powers. So proof, let me do a couple of quick cases. Consider x plus h squared and x plus h cubed. I just want to do these as an example before I do the general case. X plus h squared, you should know how to square this. You get x squared, you get plus 2 times this, so 2xh, plus h squared. Great. What's x plus h cubed? Well, x plus h cubed is x plus h times x plus h squared. That's x plus h times this, so times x squared plus 2xh plus h squared. That's x cubed, so x times x squared, plus x times 2xh, so we get plus a 2x squared h, plus x times h squared, plus h times x squared, plus h times 2xh, so plus 2xh squared, and then plus h times h squared, so plus an h cubed. You may have seen this expansion before. This is called a binomial expansion because there are two terms here and it's raised to a power. If we collect terms, we get, this is x cubed. The x squared terms, I have a 2x squared h. Here's hx squared, but that's the same as x squared h. So we get a 2x squared h plus an x squared h. That's a plus 3x squared h. Plus there's an xh squared and a 2xh squared. That's plus 3xh squared. And then plus h cubed. All right. What's important about this? What's important is just the first two terms that we're seeing each place. It's true that there's a whole binomial expansion and you can identify all the coefficients that you get, but we don't need that. We have this, and we have this. What do you see here? You see that when you raise a binomial, x plus h, to a power, you start with powers of x of the same power you have here. So you start with x cubed, no h's. And then as you go down, the power of x goes down 1, the power of h goes up 1. The power of x goes down 1, the power of h goes up 1. The power of x goes down 1 more from x to the 1 to x to the 0, which is 1. Times h cubed. And then the question is, where do these coefficients come from? Those are called binomial coefficients, but all we really need, and we'll see this in a minute, is this first one. And it's always just in. When the exponent is 2, there's a 2 there. When this exponent is 3, there's a 3 there. It's not going to matter to us what the rest of the coefficients are. So what I'm claiming is that one can prove by induction, we won't, that this is x to the n plus n x to the n minus 1 times h. So the power of x went down by 1, the power of h went up by 1. The coefficient here is whatever the exponent was. And then there's other stuff. What's the other stuff? The other stuff is you've got powers of x and powers of h, but after this, all the powers of h are 2 or bigger. Right? Because in the next term, the power of x will go down by 1, the power of h will go up by 1, so you'll have an h squared. And every term after that will have a power of h that's h squared or higher. So I'll just write that we get something that's h squared, and if you factor the h squared out of those terms, h squared times some function that'll have x's and h's in it, where this thing is a polynomial in powers of h with coefficients involving x. Of course, we could think of it the other way, as a polynomial in x whose coefficients involve h, but that's not how I want to think of it for what we're about to do, with coefficients involving x. So, for instance, for x plus h squared, we're saying x plus h squared is, well, it's x squared plus 2xh plus h squared times 1. So when n is 2, this function, p of xh, would be the constant function 1, which is kind of boring, but for x plus h cubed, then what we see up here, actually I'll just write it up here, you get the x cubed plus you get the 3x squared h plus, and then if you factor an h squared out of here and here, you get plus h squared times 3x plus h. So when you get to x plus h cubed, yes, you get x cubed plus 3x squared h plus h squared times this function of x and h, which is 3x plus h. All right. So we need this. This is what we need. And once we have that, the proof of the power rule is easy. It's not a coincidence that the power rule says the derivative of x to the n is n x to the n minus 1, and you see an n x to the n minus 1 there. That's exactly where it's going to come from. So, how do you prove the power rule? The derivative is the instantaneous rate of change. It's the limit of the average rates of change. It is that limit. So, what is the derivative of x to the n? It is the limit as h approaches 0 of this with the x replaced by x plus h to the n minus that x to the n all divided by h. But now we use that x plus h to the n has that form that I just wrote. So this is the limit as h approaches 0 of, you get an x to the n plus n x to the n minus 1 times h plus h squared times this function p of xh minus x to the n. And it's all divided by h. What does this give you? You have an x to the n here and a minus x to the n there. Those cancel. The other terms have h's in them, and you can divide by the h, and you quickly get, this is the limit as h approaches 0 of, so these canceled. We canceled an h here and here, so we get n x to the n minus 1 plus h times p of xh. H is our variable. It's what's changing here. X is some fixed value, at least while we're calculating the limit. So this is just a constant as far as h is concerned. So the limit of this part is just, we split up this limit as a sum. The limit of this part is n x to the n minus 1. And then you get plus this part. As h approaches 0, this h approaches 0. And you might think, oh, well, then it doesn't matter what p of xh does. 0 times anything is 0. Yes, but to know that the limit of the product is the product of the limits, you have to know that the limit as h approaches 0, p of xh exists. But that's true, because p of xh is a polynomial in h, which is continuous. And so as h approaches 0, this part just approaches p of x0, which is some number that exists. And so, yes, because h approaches 0 and this approaches something, this limit is 0, and we're just left with n x to the n minus 1, which is what we were trying to show. So now we have the power rule. We can differentiate any power of x, so find the instantaneous rate of change of any integral positive integer power of x as fast as we can write, without ever doing that algebra again. The whole point of developing the rules is to do this once for kind of general functions with a general exponent and never have to do this algebra again. I should say that we also kind of think of this as being true when n is 0. Let me explain that, because it's something, a convention that is handy to use throughout much of calculus. So what we've just shown is the derivative of x to the n is n x to the n minus 1. This is true if n is a natural number, so in particular greater than or equal to 1. But we actually have a couple of problems, even when n is 1 and when n is 0. So when n is 1, So we would be saying the derivative of x to the 1, which is just x. So the derivative of x, which is the derivative of x to the 1, is 1 times x to the 1 minus 1. That's 1 times x to the 0. Well, yeah, and you may say, well, that's fine, because we know the derivative of just x. We had this in the last chapter. The derivative of x is just 1, and x to the 0 is 1. Well, x to the 0 is 1 if x isn't 0. If x is 0, 0 to the 0 is technically undefined. But yes, we just kind of agree that as far as the power rule is concerned, when n is 1 and we get x to the 0 here, we mean that it's 1 even if x is 0. Because this function is certainly differentiable when x is 0 and you still get 1. So here we need that we're agreeing that at least as far as just so that we can say the power rule is true when n is 1, we have to adopt the convention that x to the 0 in the power rule equals 1 even if x equals 0. I am not saying that, yes, in this class, in this course, 0 to the 0 is defined to be 1. I'm just saying that in the power rule, that when you get x to the 0, you should interpret it as 1 regardless of the value of x, if you want this rule to be true when n is 1. On the other hand, you could just consider this a separate rule, but that's kind of annoying. We have a similar thing if we actually take the derivative of x to the 0. What should this mean? Well, if x to the 0 means 1, when we're dealing with the power rule, then of course the derivative of 1, 1 is a constant, its derivative is 0. So this should be 0. Of course, if we applied the power rule when n is 0, what we get is that this should be 0 times x to the minus 1. So it's 0 times something, and we're saying that should be 0. Fine, except what if x is 0 again? All right, if you want to say the power rule is true even when n is 0, then you need to have another convention that, all right, not only does x to the 0 mean 1, but 0 times x to the minus 1 needs to mean 0 even when x is 0. So if you understand those degenerate cases that, yes, when x is 0, you have to interpret this in a way that you're not saying that 0 over 0 is defined. I'm not saying 0 to the 0 is 1. I'm saying that when you're reading the power rule, if you want to apply it, that's how you have to think of these things. With those conventions, yes, the power rule is true for n an integer greater than or equal to 0, and that's usually how I'll use it. Knowing the power rule is especially convenient or nice in combination with two things that we proved in the last chapter, namely that if you take the derivative of a constant times a function, we had that if you take the derivative of a constant times a function, that's the same as you can pull the constant out and multiply it times the derivative of the original function. We also had, I didn't prove it, but that if you have the sum of two functions and you take the derivative, it's just the sum of the individual derivatives. If you combine these two things, you get a property that's referred to as linearity. We say that differentiation is a linear operation. So linearity, which gets used in calculating derivatives all the time, says if you've got some constant times a function plus some constant times another function, and you want the derivative, you split up the sum, like this tells us we can do, and you pull out the constants, like this tells you can do. So you get a times f prime of x plus b times g prime of x. Differentiation is linear. It's a linear operation. If you iterate this to more sums and pulling out more constants, and you combine it with the power rule, you'll be able to differentiate every polynomial. So we can now differentiate every single polynomial as fast as we can write. So you look at derivatives of polynomials. suppose you have, it doesn't matter, 5x to the 7th minus 3x to the 6th plus, I'll leave out an x to the 5th term, how about a plus pi times x to the 4th plus 7x cubed, I'll leave out a squared term, minus x plus the square root of 2. And we want the derivative of all of that. What a mess. If we had to do this using the definition of the derivative, it would take a long time. But linearity says that we can split up all these sums and pull out all the constants. Oh, because I should have said this explicitly, because b can be negative, right? If you had a subtraction here, you could have a subtraction here. Just think of it as adding the negative b. So a lot of places where you see linearity, they'll put a plus or minus here and a plus or minus here. It's certainly true. Whether you think of it as the sum of adding something negative or subtracting, it doesn't matter. This is true. So we can split up sums and differences and pull out constants. And what happens? We get, by linearity, this long derivative breaks up into the derivative of this part minus the derivative of this part plus the derivative of this part plus the derivative of this part minus the derivative of x plus the derivative of the square root of 2. But then the derivative of this part, by linearity, you can pull out the 5, and you're just left with having to calculate the derivative of x to the 7th. But the power rule tells us how to do that. So what do you get? You get 5 times 7x to the 6th, where we use the power rule. The exponent comes down, you subtract 1 from the exponent, minus 3 times the derivative of x to the 6th, 6 times x to the 5th. The power comes down as multiplication, you subtract 1 from the exponent. Pi, it's just a constant. It's an ugly looking constant, but it's just a constant. You know, it's about 3.14. So plus pi times the power rule, 4x cubed, plus 7 times 3x squared, minus the derivative of x is just 1, and the derivative of a constant, even though it's the square root of 2, you don't do anything with the square root operation. The square root of 2 is just a constant. Its derivative is 0. And this is the derivative of that polynomial. You can simplify it. You can neaten it up a little bit, right? This is 35 and minus 18 and 4 pi and 21x squared. But we finished differentiating. This is the derivative of that complicated thing. We don't use the definition anymore. But I want to emphasize, the rule kind of disguises that it's an instantaneous rate of change. It is because the definition of the derivative is what we use to prove this rule. The definition of the derivative is that the derivative is the limit of the average rates of change. So this is the instantaneous rate of change of this function with respect to x. It's just kind of, that fact is kind of hidden because we proved this rule that we use to calculate it. All right, maybe before I do some more interesting examples, it would be helpful to have some summation notation. So some notation for writing polynomials and long sums. We'll need it later in the book, and now would be a good time to have it. So let me introduce summation notation, or sigma notation. So suppose m and n are integers, and I'll suppose that m is less than or equal to n. And then I'll suppose b of, I'll write x, but is a function whose domain includes, I want it to include all the integers between m and n, including m and n, whose domain includes all integers I, such that m is less than or equal to I is less than or equal to m. So b is some function whose domain at least includes these integers. It might be bigger, it might be exactly that, it might just be all integers. Then we write this, and I'll say the right words, this is a capital sigma. We write this, which is, you read it, the sum as I goes from m to n of b of I. So this notation, it means add up all of these things as you let I first be m, and then you let I be m plus 1, and then you just keep letting I get bigger and bigger until it reaches n, and you add all of those together. That's what this sigma means, add. So, so it means you take b of m plus the next, you let I be 1 bigger, b of m plus 1, plus, and you just keep adding until you get to, well, just before n, you would be at n minus 1 plus bn. It means that sum. This is called sigma notation or summation notation. It's just handy for writing long sums like that polynomial that I wrote over there, summation notation. So as an example, if you had the sum as I goes from minus 2 to 3 of I squared, what does that mean? It means first I is minus 2, and you plug it into here and you square it. So you get minus 2 squared, and you add to that what you get when I is minus 1 squared, plus I goes up again to 0, 0 squared, plus 1 squared, plus 2 squared, plus 3 squared. I don't really care what this adds up to. I guess I'll work it out. But the point is that summation, that thing with the sigma in it, the sum as I goes from minus 2 to 3 of I squared, means this, whatever it comes out to be. What is this? 4, 5, 6, 10, 19. All right. Okay, that's summation notation. What's nice about summation notation? Well, lots of things, but the reason I'm doing it right now is so I can write in general what the derivative of a polynomial looks like, although this example was probably very clear. In general, if you have a polynomial function is always of this form. In summation notation, it would look like this. You let I be 0, and you get a to the 0, x to the 0. And again, we are assuming that x to the 0 means 1, even if x is 0. It's just, we are not claiming 0 to the 0 is defined. It's just handy that it fits into this notation for us to think of x to the 0 as meaning the function that's always 1. So you get a to the 0 times 1. Plus, you add to that what you get when I is 1, plus a sub 1, x to the 1, but that's just x, plus a sub 2, x squared. So what this plus, and then the final term would be a sub n, x to the n, where the a's are some constants. This is just a convenient way of writing polynomials. This would be a polynomial of degree n, assuming that a sub n is not 0. All right. So the point is that now we can write the derivatives, the derivative of a general polynomial very easily by combining linearity and the power rule. The derivative of this general polynomial, the derivative of this constant term will be 0. And then the derivative of this term will be a sub 1 times the derivative of x, which is 1. So you'll get an a sub 1. So our indexing, the I is called an index, will start at 1. It's the sum as I goes from 1 to n of, you can just look at each term. The fact that the derivative of the sum is the sum of the derivatives means the derivative of this sum, you just add up the derivatives of these, but then you can pull the AIs out because the derivative of a constant times a function is just the constant times the derivative function. And then the power rule tells us that the derivative of x to the I is I, x to the I minus 1. So this is what you get. The derivative of this general polynomial is this. AI times I times x to the I minus 1. Then you sum those as I goes from 1 to n. Again, we are assuming the convention that when I is 1, so that this is x to the 0, that by x to the 0, we mean the function that's always 1. Great. So now we know how to differentiate every single polynomial. So why don't we do some examples? All right. In the last chapter, we had a problem about a spherical balloon. And we wrote the radius of the balloon as a function of the volume and looked at the rate of change of the radius as the volume changed. I'm going to look at the same balloon, the same spherical balloon, but now I'm going to have the volume as a function of the radius, which is kind of the more normal situation. So I have a spherical balloon. Its volume, since it's a sphere, 4/3 pi r cubed, where V is the volume in, I'll say in cubic inches. And R is the radius in inches. Okay, the question is, what is the instantaneous rate of change? So the IROC, the instantaneous rate of change of the volume with respect to the radius. When the radius is 5 inches. Well, this would have taken us some effort in the last chapter, but it's ridiculously easy now. The instantaneous rate of change, the derivative. How easily can we find, with respect to R, we're being asked for dV/dr. We're being asked for it when R is 5, but you calculate dV/dr at all R values first, and then plug in that R is 5. So what's dV/dr? Well, V is 4/3 pi r cubed. 4/3 pi r cubed. 4/3 pi is a constant. So the derivative of this constant times this function, you just pull out the constant, so you get 4/3 pi times the derivative of r cubed with respect to r. But that's the power rule. The exponent comes down and you subtract 1 from the exponent. 3r squared. The 3's cancel, and you get 4 pi r squared. The units here, the units of V divided by the units of r. This is cubic inches per inch. That is, the instantaneous rate of change of the volume with respect to the radius is 4 pi r squared cubic inches of volume per inch of radius. So that's what you get at any r value. We're supposed to do this when r is 5. dV/dr. When r is 5, you just get 4 pi times 5 squared. 25 times 4, 100 pi. Cubic inches per inch. And that's it. That's all you do. Okay. Let's go back to another example. from the last chapter. We had widescreen television. So we had a 16 by 9 television. And we determined that the area of such a television as a function of its diagonal length was, actually I have to look up the number, 144 over 337. 144 over 337 times d squared, where a is in square inches, and d is in inches. Great. So what's the derivative? What is the instantaneous rate of change with respect to d? Instantaneous rate of change of a with respect to d. I'll just say for any d instead of with respect to d. All right, what's the derivative of this with respect to d? What you don't write in a problem that already has d's in it is the notation I used over here. Over here I use Leibniz's notation, this notation that looks like a fraction. I'll remind you, this is not a fraction. There is no separate quantity dv that's being divided by some quantity dr here. It's just notation. You don't even read this as dv divided by dr. It is, you say dv dr. But one problem with this notation, aside from the fact that it makes people think it really is a fraction, it is a limit of fractions, but it itself is not a fraction. This notation is bad when one of your variables is already little d because it uses little d's and it would look terrible to write. And we'd have to write something like dA dd, which really you could write, but it would be kind of confusing. So I suggest that if d is a variable, little d is a variable in your problem and you're dying to use this notation, change that variable name. Call it something else, at least in the middle of your calculations, and switch it back to a d at the end or something. All right. So we'll use notation with the primes. A prime of d, the derivative of this is a constant. You just pull it out. The derivative of d squared. By the power rule, the 2 comes down. You subtract 1 from the exponent. You get 2d to the 1. That's just 2d. We quickly get 144 over 337 times 2d. Or what's the same thing? 288 over 337d. Units, square inches per inch. That's the instantaneous rate of change of the area of the television with respect to the diagonal length of the screen. And as we discussed before, as we saw before, as d gets bigger, this rate of change gets bigger. So if you start with a bigger television, one with a bigger diagonal measurement, then the rate of change in the TV as you add inches to the diagonal measurement, so if you were thinking, maybe I should get a slightly bigger TV, the rate of change is bigger for a bigger d. So if you increase the diagonal measurement of a bigger widescreen television, you actually add more inches than if you add the same number of inches to a small screen television. But it's in a way, that's counterintuitive because a lot of us think, like I think, yeah, for a small TV, if you add some inches to the diagonal, it makes a bigger difference. Well, when we think that, we don't really mean a bigger difference. We mean it increases the percentage. As a percentage of your current area, it causes more of an increase when d is small. That is, if you have a small television and a small screen television, and you add a couple of inches, or a few inches. Maybe you double the area of your television when it wouldn't double the area of a much bigger TV. Yeah, you might add more actual inches in the big TV than to the small TV, but as a fraction of the original size, it's much bigger when D is smaller. How do we see that? Well, it's easy for us now. We can define the fractional rate of change. The fractional rate of change of A with respect to D. As being what? Well, the rate of change of A with respect to D, but then divide by A of D. So take your rate of change of the area with respect to the diagonal length and divide by the area so that we can see kind of what fraction you're going up by. If you do this, you get well, let me do a more general thing. Here we used a 16:9 television. We could do the general case where A is any constant times D squared. This constant for us was 144 over 337 because we were using a widescreen TV. If you were using a full screen TV, so a 4:3 TV, this constant would be different. But what we'll see is that in the fractional rate of change, the constant drops out, so it doesn't matter what it was. This calculation would be the same for a widescreen television and a full screen television. So what do we get for A prime of D in this case? This is a constant, and then the derivative of D squared by the power rule, 2D to the 1, but that's 2D. So you just get 2CD. So this would be 2CD, and then A of D is CD squared. The C's cancel. You can cancel one of the D's. You get 2 over D. The units here are a little weird. This is square inches per inch, and we divide it by square inches. So the units come out as just being in per inches, so 1 over inches. But what do we see? It's 2 over D. Regardless, the C dropped out. So widescreen television, full screen television, doesn't matter. And because we got 2 over D, you see that if D is smaller, this is a bigger number. When D is bigger, this is a smaller number. So the actual fractional increase in the size of a television is bigger for smaller televisions. And this kind of matches our intuition that, yeah, if you're considering a small screen television, if you just go up a few inches, you get a much bigger television, bigger as a fraction of the other size television. All right. Let me look at one last example in this section. I want to go back to concavity of a graph, where we can now do a calculation of some interesting concavity. So where the graph is concave up and where it's concave down. We looked at that in the last section of the first chapter. But let's look at it again now that we have the power rule and can actually do some calculations easily. So let's look at y equals some polynomial in terms of x, and the polynomial I want is x plus 2 times x minus 1 times x minus 3. For us to use the power rule on this, we are going to, and linearity, we are going to need to multiply this out. So let me go ahead and do that. You get x plus 2 times this part. You get x times x, you get x squared. The cross terms, you get a minus x minus 3x, so minus 4x. Plus minus 1 times minus 3, so plus 3. And then you multiply that times x plus 2. So you multiply x times x squared, you get x cubed, plus x times minus 4x, so you get a minus 4x squared. Plus x times 3, so plus 3x. And then 2 times x squared plus a 2 times x squared plus 2 times minus 4x, so minus 8x, plus 2 times 3, so plus 6. And then collecting terms, you get an x cubed squared terms. We have a minus 4x squared and a plus 2x squared. That's a minus 2x squared. X terms, a 3x minus 8x, so a minus 5x, and a plus 6. So let's look at this polynomial and its graph. Of course, if you do this on a computer or on a graphing calculator, you can have your device draw a very accurate graph on the board. I'm just going to sketch it. And it's one of the reasons that I had started with this factored. I at least know the 3 zeros of this. So it's when x is minus 2, when x is 1, and when x is 3. So I at least have those points. So let's put a... Okay, this graph roughly looks like, here's minus 2. It roughly looks like this, very roughly. So it has a 0 when x is minus 2, a 0 when x is 1, and a 0 when x is 3. All right, so what is it I'd like to look at? Well, we can see in this graph, and we will talk about graphing problems more later in the book, but we can see in this graph that the slope of the curve is positive until around here, right? If you look at the slopes of the tangent lines. Right? Remember, the derivative geometrically is the slope of the tangent line, or we just say the slope of the graph, or the slope of the function. The slopes are all positive here, here. It seems like the slopes become 0 here, and then they become negative over here. So you can see whether the first derivative is positive or negative, depending on whether the slope is positive or negative. So depending on whether the graph is roughly going from the lower left to the upper right, that would be a positive slope, or from the upper left to the lower right, this would be a negative slope over here. And then, as we saw before, the fact that this graph is kind of cupped downward, so concave down here, means the second derivative is negative. The slopes are decreasing, so big positive slope, smaller positive slope, 0 slope, negative slope. The slopes decrease until around here somewhere. And then they start, this is not supposed to do this weird thing right here. And then the slopes start increasing, and they're negative, less negative, so that's a bigger number, less negative, 0, and then positive. And so, yeah, over here you see a graph that's concave up. So that's where the slopes are increasing, which means the second derivative is positive. Can we actually calculate where the first derivative is positive and negative, and where the second derivative is positive and negative, so that instead of just trying to see these places on the graph, we can actually calculate exactly where they occur? Yes, it's easy for us now. Here's our function y. We know how to calculate its derivative from the power rule. It's easy. We get that y prime, actually let me write y here. It is x cubed minus 2x squared minus 5x plus 6. So y prime, the power rule, 3x squared minus 2. That constant just goes along for the ride, and you apply the power rule to x squared. You get a 2, x to the 1, so that's just a 2x, but it's minus 2 times 2, so minus 4x. The derivative of minus 5x, you just get minus 5 times the derivative of x, which is 1, the derivative of a constant 0. So this is the derivative of our function. Y double prime, so the second derivative, the derivative of the derivative, again, you get 3 times the derivative of x squared, the derivative of x squared, 2x by the power rule. So we get 6x. And then the derivative of minus 4x is just minus 4 times the derivative of x, minus 4 times 1, the derivative of constant is 0. So here's what we get for the first and second derivatives. It's easy. The second derivative is 6x minus 4. Where is that positive and where is it negative? Well, let's look at where it's 0. It's 0, so 6x minus 4 equals 0 when x is 4/6, or what's the same thing, 2/3. It's easy to calculate the first derivative, easy to calculate the second derivative. It's easy to find where the second derivative is 0. It's when x is 2/3. So, okay, the second derivative is 0 when x is 2/3. How do you know where the second derivative is positive and where the second derivative is negative? This is a continuous function, and it's defined on the entire real line. Continuous functions defined on intervals satisfy the intermediate value theorem, which says, well, in particular says that if the function is negative at one x-coordinate and positive at another x-coordinate, then there was some x-coordinate in between those two where the function is 0. So why is that useful to us? Suppose we want to know where this function is positive and where it's negative. You find where it equals 0 at 2/3. So here's 2/3. And then you just pick any x-coordinate you want, less than 2/3. And you see whether the function 6x minus 4 is positive or negative there. Like when x is 0, this is negative. I claim that that means that y double prime is negative everywhere less than 2/3. And we see that in the graph because the graph is concave down, but maybe it does something stranger over here. Why does it imply that? Because suppose we check two x values over here, and at one of these x values the y double prime is positive, and another one y prime is negative. Y double prime is negative. If y double prime goes from positive to negative over here, it has to hit 0 someplace in between. But we already found all the places where it's 0, 2/3. So yeah, it can't switch signs anyplace else. The only place that continuous functions defined on intervals can change signs are where they hit 0. So you just check in between the zeros, plug in any number you want, and see whether you get something positive or negative. So when x is less than 2/3, we get something negative. When x is greater than 2/3, like 500 billion, this is certainly positive. So it's positive everywhere for x greater than 2/3. And so we see what we see in the graph, that y double prime is negative when x is less than 2/3. So the graph is concave down. When x is greater than 2/3, y double prime is positive, and we see the graph is concave up. We can also analyze the slopes and whether the slopes of the tangent lines or the slopes of the graph are positive or negative. It's a little tougher because we have to use the quadratic formula to find where this is 0, but we can do that. We all know the quadratic formula. So you set 3x squared minus 4x minus 5 equal to 0, and you solve. Quadratic formula, x is negative b, so negative 4, plus or minus the square root of b squared, that's minus 4 squared, minus 4 times a times c, all over 2a, which is 2 times 3, so 6. So we get 4 plus or minus the square root of 16 plus 60, all over 6. This is 4 plus or minus the square root of 76 over 6. 76 is 4 times 19, so we can factor out a square root of 4 and as a 2, so the square root of 4 is 2, so this is the same as 4 plus or minus 2 times the square root of 19 over 6. And so that's, you can divide the numerator and denominator by 2 if you want. This is 2 plus or minus the square root of 19 over 3. All right. Approximately, 19 is a little less than 25. square root of, or it's a little bigger than 16, so the square root of 19, somewhere between 4 and 5. So what are we getting for the roots? Something between 4 and 5. 2 minus 4 would be minus 2/3. So, right, 2 minus 4 over 3 would be minus 2/3. 2 minus 5 would be minus 1. So somewhere between minus 2/3 and minus 1. So yeah, that's where we're seeing this horizontal tangent line, this slope 0. This is really 2 minus the square root of 19 over 3. Where are we finding this other horizontal tangent line? It would be at 2 plus the square root of 19 over 3. So this is 2 plus the square root of 19 over 3. What is that? Again, this is between 4 and 5. So this is between, the numerator is between 6 and 7. So, a little bigger than 2. It's a little bigger than 2. Okay. And, right, so what happens to the slopes? Well, the slopes then, I didn't mean to erase that. The slopes then can only change signs at these two x coordinates. So when x is less than 2 minus the square root of 19 over 3, we should see that y prime is positive because the slope is positive. What's my favorite number less than 2 minus the square root of 19 over 3? Negative 300 trillion. If x is negative 300 trillion, then you get 3 times something very large, because you get negative 300 trillion squared. The squared will get rid of the minus sign, and then you'll have 300 trillion squared. That's much bigger than this part. You get something very positive. So certainly the slope is positive here. Instead of picking negative 300, something absurdly negative, you could just pick negative 2. When x is negative 2, you get 3 times 4, 12, plus 8, so 20 minus 5, 15. In any case, something positive. So the slope is positive everywhere for x less than 2 minus the square root of 19 over 3. So that's why you see this positive slope. Between 2 minus the square root of 19 over 3 and 2 plus the square root of 19 over 3, my favorite x value is 0. When x is 0 in y prime, you get 0, 0 minus 5, you get something negative. And yes, we see the negative slope between here and here in the graph. The graph goes from the upper left to the lower right. It's decreasing. And then, what's my favorite x coordinate greater than 2 plus the square root of 19 over 3? Either pick something absurdly huge or pick 4. When x is 4, you would get 16 times 3, 48 minus 16. So what's that? 32 minus 5, 27. You get something positive. So yes, we get the positive slopes that we see over here in the graph because we see it increasing. All right, those are some uses of the power rule and linearity. We'll use them throughout the rest of the book. Next time, we'll look at the product rule and the quotient rule that tell you how to take derivatives of products of functions and quotients of functions.